Welcome to the Deep Dive. We're the place you come to really get under the hood of the latest research, pulling out the key insights you need. And today, well, we're tackling something you've probably thought about. How do scientists actually know if what you eat affects your health?
Yeah, it sounds simple, but it's surprisingly complex, especially when you try to pinpoint the effect of one specific nutrient versus another.
It really is. One of the biggest hurdles in nutritional studies is trying to separate the impact of something like protein, from just the total calories someone eats.
Exactly. It's a huge challenge. Researchers have been banging their heads against this wall for years. So, okay, let's unpack this. Today we're doing a deep dive into a really interesting paper. It's called Applying Compositional Data Methodology to Nutritional Epidemiology by Maria Léa Corrêa Leite.
Hmm.
And it introduces, well, what looks like a pretty major step forward in statistical methods. It promises clearer answers, cutting through some of that historical confusion in diet studies.
It really does aim to clean things up. So, our mission today. First, understand this tricky data problem. Then, explore this elegant new solution. And finally, see what kind of surprising insights it gives us about diet and conditions like metabolic syndrome. Sound good?
Let's do it.
Okay, so to really get the problem, think about your daily diet like a pie chart. You've got slices for protein, fat, carbs,
Right.
and the crucial thing is those slices always add up to 100% of your energy intake. If you decide to eat more protein, you have to eat less of something else, right? Assuming your total calories don't change.
Exactly. And that part's of a whole thing. That's what makes nutritional data compositional.
Mhm.
It's not just about how much protein, but how much protein relative to fat and carbs within that fixed energy budget.
Got it. So it's all interconnected.
Precisely. And what's fascinating, or maybe frustrating, depending on how you look at it, is that this compositional nature is exactly why standard statistical methods often fall short here.
Why is that?
Well, think about it. Standard methods are usually designed for variables that can, go up or down independently.
Yeah.
But protein, fat, and carbs, they're constrained. They always sum to that total energy, so they only give you relative information.
Ah, okay. So trying to use normal stats is like forcing a square peg into a round hole.
That's a good way to put it. You try applying standard tools, and because of that constraint, they can misinterpret how things vary together. You end up with what statisticians call a negatively biased covariance structure. It basically warps the picture.
Right.
The statistician Jay Aitchison actually warned about this way back. He said using standard methods here could lead straight to misleading results and conclusions.
So the tools themselves were part of the problem because they weren't built for this kind of interconnected data.
Exactly that. You just can't easily untangle the effect of, say, more carbs from the effect of total energy using standard multivariate analysis. They're woven together.
Okay. So if the usual methods don't work well because the data is all about these relative parts, what's the alternative? This paper you mentioned points towards Aitchison's work on log ratio transformations.
That's where things get really interesting.
Tell me more.
The core idea is actually quite elegant. It says that any meaningful statistical analysis of a composition like our diet has to be done using ratios of the parts, not the absolute amounts of the parts themselves.
Ratios. So like the ratio of protein to carbs or fat to protein.
Exactly. Think about the proportion of protein compared to fat changing, rather than just the grams of protein, which is always tied to the total calories anyway.
Okay, that makes intuitive sense.
Yeah. Now, there were earlier attempts to do this, like something called additive log ratio, or Euler, and centered log ratio, Clearo transformations. There were steps in the right direction, but they had their own technical problems.
Yeah.
Things like not preserving mathematical distances correctly or creating statistical headaches called singular covariance matrices.
So close, but no cigar. What was the real breakthrough then?
The big step forward is the isometric log ratio transformation, or ILVR.
Okay.
It's based on some quite advanced math called Aitchison geometry in the simplex. But the basic idea is it provides a way to transform that constrained compositional data, our diet percentages, into a new set of variables.
And what's special about these new variables?
They live in a normal, unconstrained space. Think of it like taking data points spread across the surface of a ball and accurately mapping them onto a flat piece of paper without distorting the distances between them.
Wow, okay.
The IL transformation creates these real orthogonal coordinates, which means we can finally use standard statistical methods on these transformed variables, and they work properly. And crucially, it does this while preserving all the important relational information from the original data.
That sounds Huge. So the ill method lets us map the diet data onto a new space where standard stats work fine.
You got it. And the variables it creates allow for full inferences about each element of dietary composition and adjustment by total energy intake.
Meaning we can finally ask, what's the specific effect of having a higher proportion of protein in your diet holding total calories constant?
Precisely. You can isolate that effect. It makes the analysis way more robust and, importantly, easier to interpret correctly. It's a real game changer.
Okay, so theory is one thing. How did they apply this in the paper? You mentioned the Italian bullet eye study.
Yes, exactly. They took this powerful ill method and applied it to real data from that study. It was done back in the early 90s, 1992-93,
Right.
and involved nearly 1,150 middle-aged people, men and women,
Yeah.
aged between 40 and 74.
And the goal was to look at macronutrients, protein, fat, carbs, and their link to metabolic syndrome.
Metabolic syndrome, or MSC, which is a cluster of conditions that increase risk for heart disease, stroke, diabetes. And it wasn't rare in this group either. About 47% of the men and nearly 30% of the women had it.
It's a really relevant health issue. How did the ill method help analyze that link?
Well, essentially, by applying the ill transformation, they created new variables from the protein, fat, and carb data. These new variables are mathematically independent, free from that parts of a whole constraint.
Okay.
So for instance, one of these new ill variables would capture the information specifically about the proportion of protein in the diet, allowing them to test its effect on MS risk separately from the effects of fat, carbs, or even total calories.
This sounds like it could definitely lead to some clearer, maybe even unexpected findings. So what did they find when they looked at macronutrients and MS risk using this method?
Okay, this is where it gets really fascinating. They first looked at the simple three-part composition: proteins, fats, and carbohydrates. And they analyzed it in what's called an isocaloric context.
Meaning keeping total calories constant.
Exactly. So looking at the effect of shifting the proportions without changing the total energy, and they found, drumroll please, that the odds of having metabolic syndrome increased as the dietary protein content went up.
They increased with higher protein.
Yes, statistically significant increase. And conversely, they found an inverse relationship between the odds of MS and the relative amount of carbohydrates in the diet.
So higher carbs were linked to lower odds of MS.
That's what the data suggested. P 0.004. Higher carb proportions seemed protective in this context.
Wow. Okay. That definitely pushes against some popular diet narratives today that really emphasize high protein, low carb.
It certainly does. It suggests that when you hold calories constant, simply swapping carbs for protein might not be beneficial for metabolic syndrome risk and could potentially be detrimental.
That's really interesting. What about total energy intake itself? Did that show a link?
Also very interesting, the coefficient for total daily energy intake when adjusted for composition was not statistically significant, P 0.818.
So in this analysis, the balance of macros seemed more strongly linked to MS risk than the total number of calories consumed.
That's what this specific analysis points to. It really highlights how important it is to disentangle composition from total energy, something the ill method allows us to do properly.
Okay, but they didn't just stop at the three main macronutrients, did they? They looked at a more detailed breakdown.
That's right. They also analyzed a 7-part composition: animal protein, vegetal protein, saturated fat, monounsaturated fat, polyunsaturated fat, starch, and sugar, getting much more granular.
And what came out of that finer-grained analysis? Did it tell a similar story?
Broadly, yes, but with more nuance. The odds of having MS were associated with diets higher in animal protein, though that was borderline significant, P 0.053, and interestingly, even more significantly associated with diets high in vegetal protein, P 0.024.
Both animal and plant protein linked to higher MS odds.
In this analysis, yes. And on the flip side, the odds of MS were inversely associated with starch content, P 0.0122, and also sugar content, P 0.005.
Wait, sugar too. Lower odds of MS with higher sugar content alongside starch. That's another finding that might raise some eyebrows.
It might. But it's important to remember this is about relative proportions within a fixed total energy. And the paper notes these findings, particularly around carbs and protein, actually align with results from some other large prospective studies.
Ah, okay, so it's not totally out of left field. It just reinforces those previous findings with a more statistically sound method.
Exactly. What the EEL method brings is that formal mathematical appropriateness, as the paper puts it. It helps confirm those associations are likely real and not just artifacts of older, less suitable statistical techniques that struggled with the compositional data.
Right. So let's talk about those older methods. How does this Iller approach really stack up against how nutritional epidemiology used to be done? The paper mentions things like residual models.
Yes, visual models were a common approach. The idea was to statistically adjust nutrient intake for total energy. But the big problem was interpretation. The coefficients you get from those models don't really represent the effect of adding more of a nutrient.
Mm.
They represent the effect of substituting one calorie source for another, often in a way that's hard to pin down precisely. Plus, these models often suffered from statistical issues like heteroscedasticity.
Which means the errors weren't consistent.
Yeah, the variability wasn't uniform. Think of it like trying to measure things with a wobbly ruler. It could lead to finding connections that weren't really there, what they call spurious relationships, false alarms.
Okay, so residual models were tricky to interpret and potentially unreliable. What about other methods? They mention complete partition models.
Right, those use the absolute amounts, like NaCal per day for each nutrient. The issue there is that approach completely masks the compositional nature of diet,
It ignores the pie chart aspect.
pretty much. And that introduces huge potential for confounding. For example, we know that often people eating fewer calories, maybe for weight loss, tend to eat relatively more protein, and people eating more calories often have diets richer in saturated fat or starch. These natural correlations get tangled up in the analysis, making it incredibly difficult to say what's really driving an association. Is it the protein itself, or the fact that high protein often goes with low calories? It obscures the specific role of each part.
Whereas this compositional data approach using ill.
It cuts through that. It provides that mathematical rigor and a much more intuitive interpretation when you're looking at nutrient composition while holding calories constant, those isocaloric analyses. It lets you see the effect of the recipe change, not just the overall size of the meal.
That really does sound like a critical step forward for the field.
Absolutely. If you think about the big picture, this approach finally lets researchers do what nutritional epidemiology always wanted to do: study the effect of dietary composition on health, separate from just total energy intake.
It's about the quality, the balance, not just the quantity.
Precisely. It helps us avoid those serious potential pitfalls of the older methods that might have led us down the wrong path with spurious associations. We get a cleaner signal.
So looking ahead, where could this methodology take us? The paper mentions food sources.
Yes, that's a really exciting potential application. Using ill, researchers could start looking not just at, say, total fat, but the effect of fat from different foods.
Like comparing fat from nuts versus fat from processed meats.
Exactly. Or protein from beans versus protein from red meat. It allows for studying the role of different food sources of nutrients, acknowledging that where our nutrients come from likely matters a great deal for health outcomes. It could lead to much more specific, source-based dietary recommendations.
That would be incredibly valuable, getting down to the level of specific foods and their impact within the overall dietary pattern.
It opens the door to analyzing macro and micronutrients based on their food origins, giving us a far more nuanced understanding.
So to wrap up, we've seen today how this compositional data methodology, particularly the isometric log ratio or ill transformation, is really changing the game for nutritional science.
It gives us a much clearer lens.
Yeah, clearer lens to see how specific nutrients, as part of the whole diet composition, relate to our health, separate from just the total calories we eat. It provides a much more robust way to understand how our food choices might influence conditions like metabolic syndrome.
Definitely a more refined toolkit.
It moves us past some major limitations of older methods, giving us, hopefully, more reliable insights. So here's something to chew on as we finish. We know that lower calorie diets often end up being higher in protein, while higher calorie diets are often richer in saturated fat or starch. Now that we have analytical tools sophisticated enough to untangle these natural correlations, how might this change things? Not just for scientists studying diet, but for you. How might this lens shift how you think about your own plate, focusing maybe less on just the calorie count and more on the actual composition, the ratios, the balance of what's on there? What if that balance holds more power than we previously realized?